as the x and the y-axis. So let's call this axis the y-axis and the other one x-axis. So this is the y and the x. Now, say you wanna describe a certain point in the circle. There are a few ways to do it. So one would be, you could think of suppose you want to describe this point. Imagine you started from this place and you run away, you run across, and suppose you reach this place. And if you want to describe this specific location, what you could do is you could think about the x and the y coordinates of this place. So imagine this length is 1/2, and this length is square root of 3/2. What you could do is you could describe this location, you could describe this x, this position, as -1/2 comma square root 3/2. You could describe this position as the coordinates of the coordinate system. So because we're going to the left of the x-axis, so it's a minus sign here, so -1/2 and root 3/2. But there's another equivalent way of doing that, and that would be using angles. So to explain what I'm saying here, when you reach here, imagine you reach here, and let me draw this with a dotted line. What I can do is that I can think of an angle that starts from the x-axis, that starts from here and reaches until this point. So let me call this angle theta. So what I can essentially do is that I can represent each point in the circle by a unique angle theta. So let's look at a few simple cases. So imagine in the circle, in the circle, you start at this place. If you start at this place, this is just going to correspond to the place where theta is 0. Now let's look at this place. That's sort of halfway between the axis. So this location would be theta is 45 degrees, and if we now look at exactly perpendicular to the y-axis, when you reach here, that's going to represent theta as being equal to 90 degrees, and so on and so forth. Now you might ask, how does this relate to trigonometry, and how does this relate to triangles in general? Now, what I'm about to say about the definitions or the sort of the introduction to trigonometry or sines and cosines would be new, but hear me out. Now think of describing any specific point. Say let's choose a specific point, or let's choose a general point like this. If you choose a general point, any general point like this, that's got an angle theta with the x-axis, well, I can think of the x coordinate, that it has. So this is the x coordinate that it has, and this is the y coordinate that it has. So if you think about it in terms of length, think of this length. If you think of this triangle, this right angle triangle, we can basically think of this base as being a certain length, and let's call it x. And we know that this point is a certain distance high above the x-axis, which we can call the y distance. Now what we can do is, for every angle, we say that this base, this represents the sine of the theta, the cos theta for this angle, and this length represents the sine theta for this angle. So to make my point a bit clear, imagine you're moving around this circle, right? So when you're at this place, and you draw this triangle, when you draw this right angle triangle, this right angle triangle is going to have some angle theta, and corresponding to this angle, this triangle is going to have a certain length for the base. and a certain length for the height. And that length for the base and the height, that we say to be the cos and the sine component of the angle. So what we're essentially trying to do is that for every given angle, we're trying to see what the lengths of the base and the height of the triangle is. So if you think of some triangle like this, another blue triangle like this, if you can imagine, the height of this triangle is going to be more than the height of the red triangle, and the base of the blue triangle is going to be smaller than the base of the red triangle. And let's call this angle alpha. And by our definition of sines and cosines now, we know that this blue length is going to be sine of theta, and this blue length is going to be, sorry, not sine of theta, sine of alpha, and this blue length is going to be cosine of alpha. And so you see, in this way, if you think about what sine and cosine represent, what you can think of them as is sine alpha, or for any alpha in general, represents the height, H-E-I-G-H-T, height of the right triangle, and cos alpha represents the base of the right triangle. But there's something you got to be careful here, is that we've assumed that we've got a unit circle here. So we know that this length is always 1. So if you think about any triangle, any right angle triangle with the hypotenuse being equal to length 1, then its height is going to be given by sine theta, and its base is going to be cosine of theta. Now, when you move around the circle, suppose you start from this place and you go around, and suppose you stop somewhere here, and if you make a right angle triangle here, you're gonna have something like this. But notice that now my length for the base is to the left of the y-axis, or essentially in the negative x direction. So the angle or the cosine of that angle is going to be negative. But that's getting into more in-depth or the more specific parts. But for now, I think it's fine for you to understand that, or fine for you to look at sines and cosines as points in circle. Imagine a point in circle, and it's going around. And for a specific angle, you want to look at the height and the base, for the height and the base of the right triangle that it makes. And the height is defined to be sine theta, and the base is going to be defined as cos theta. And that clears up a lot of things. So if you imagine, when we say, and this is a common question that a lot of students ask, is that why is sine of 0 equal to 0? And why is sine of 90 degrees equal to 1? And in a similar way, why is cos of 0 equal to 1? And why is cos of 90 degrees equal to 0? And if you look at this picture, it's quite clear now. Let's look at the case for 0 and 90 degrees, just to give you an idea of how you can understand this. So if you look at the circle, and you consider the right triangle that is made when the angle is 0, so that's going to be something like this. So that's essentially a completely squished triangle, right? And if you think about the right angle triangle, when this angle theta, when this is 0, this height is going to be 0 as well. So that means that sine of 0 is just going to be 0 from my definition. And if you look at the length of the base of this triangle, that is just going to be the radius of the circle. And so that means that and because the base is defined to be cosine of that theta, of that angle theta, we know cosine of 0 is going to be 0, because that's just the base of the triangle. And when you move across 90 degrees, when you move forward 90 degrees, when you go round, and you reach this point, and you make this angle. Let me find a different color. Yeah. Suppose you're on in the yellow line now, And you look at this right angle triangle. Well, this is just a right angle triangle, but with its base squished. It went round, it was like this first, and then it was like this. Notice how this length is getting smaller and smaller as we go, as we approach the 90-degree angle. And just when we hit 90 degrees, that base is gonna disappear into nothingness. So, and because we know that the base is defined to be cos of theta, we know cos of 90 is 0. And by similar argument, what we can think of is sine of 90 is 1, because it's just the radius of the circle. And you can think of it in it for like angles that are more than 90 degrees as well. And feel free to do so, but I think that would be a bit long for our introduction. And what I quickly want to do is also to share a similar graph that I made. So this is one of the simulations, or I don't say simulations. This is just a graphical representation of something that I made, of the other thing that I was talking about. So if you think about going around the circle at a constant speed and looking at these lengths that represent sine and cosine. So here in this diagram, let's pause at a certain angle. Essentially, this orange line is the sine of this angle theta here, and this purple line, which is equal to this the base of the triangle, is the cosine of this specific angle. And looking at our previous example, we know that when we zoom in on the triangle as we approach the angle theta being equal to 0, we see that the triangle gets squished and squished and squished until it's just like 1 unit long. And that is in a sense why cos 0 is equal to 1. And if you want to think about how the lengths change, imagine you just look at the length of this orange line as you go around the circle, right? So you see that the angle is increasing, and it reaches a maximum at 90 degrees, and then it starts to decrease, and then it reaches 0 at 180 degrees. And after it crosses 180, it's going to be negative, a height. Suppose you want to look at how this height varies as a function of an angle. So so you want to see how this length varies as you change the angle. So what we could do is that, well, we could just make a diagram like this. So if you look at the height of the sine and you plot it, you just plot the height with respect to the angle. What you're gonna get is this wavy pattern, and this is the graph for the sine function, and this is how you construct the graph of a sine function. And in similar way, what you could do is you could look at the cosine function. That would be now, instead of looking at the orange length, you look at the purple length. So let's do that. Let's find cosine of x. Yeah, and if you look at how the curve moves, they're going to be of the same type, but do notice a few differences. That when we started at angle theta being 0, the sine it started from 0 height, and the cosine it started from 1 height, like height of length 1. So they've got this difference, but essentially these waves are the same. And talking about the usefulness or the generality of the trigonometry to anyone who's interested, where would trigonometry be used? I mean, in general, in life, I would never find. There will be like very few scenarios where I need to find the angles, or where I need to find the sides of a triangle. But so what's the use of this? The students might ask that question, and to answer that, I'm going to present another simulation of mine. Well, this might sound a bit abstract, but think of something like on cannonballs, right? Think of something like cannonball's trajectory. So the tools that you learn in GCSE right now. The same sort of tools of trigonometric manipulation that you learn right now are going to be used later on in high school and in university to study the motion of anything that has got to do with these sorts of projectile motions. So think of anything that's got to do with angles. So you look at the imagine a cannonball, and you want to see how far it goes according to different angles. So if you look at a certain angle, let's say like if you look at a steep angle and you see how far the cannonball goes, and you look at a smaller angle, and you see how far the cannonball goes. How far the cannonball goes is going to be dependent on the angle, and there you're going to use trigonometry. And yeah, this might be this can give you an idea of how trigonometry is used, but still there might be some of you who are like really interested in like knowing, okay, but in real life or in something that's more in direct use to me, how would trigonometry be used? Because there's no way I'm going to be playing around with cannonballs in my life. So how would this be used? And to answer that question, I'm going to show an even more complex graph. But this is essentially so there's a lot of going on in there, I understand, but this is something that has got to do with MRI machines. That's got to do with that. That's essentially a scanning device. But the way in which MRI machines work is that at the heart of their analysis, they use the same trigonometric functions that you use. And so essentially, to give you an idea of what this complete graph represents, is that when any sorts of MRI scan is done, and by MRI I mean magnetic resonance imaging. So that's a sort of a powerful scan that's used to detect the internal organs of of patients. So what happens is that those machines, they study the motions of individual atoms, and those motions of atoms, they're modeled using the same trigonometric equations. So their model is using essentially these same functions, these same curves. And there's a lot of analysis undoubtedly that goes behind this, but at the heart of it, you might as well even find some cosine expressions here. But these are the sort of the things, even in like big things, even in complex tools, there's this idea or this use of trigonometry that's quite prevalent. And I hope that answers your questions. And to talk more about these sorts of simulations or these sorts of interactives that I've prepared, I encourage like every one of you to like try out these websites, in particular Dismos and GeoGebra, because like I started my journey with mathematics in similar fashion. My first graph, it's right here. My first graph. This is the first interactive that I made. It's a simple graph. There's nothing. There's a curve. There's a parabolic curve, and there's a few lines, and then there's a few points. And when I made this, I was so happy. I was so excited. There was like something that I could play with, and there was something that I could interact with myself. And gradually, with more as I spent more time, I got more excited about it, and I got more proficient in making these graphs. So then I started making a bit more complex graphs as these, and then I proceeded to make these sorts of animations and essentially the final hallmark would be even making diagrams with mathematics and the sort of using curves and so using just mathematical functions to essentially draw pictures. And if you look at any of the equations of these curves, at the heart, they've got trigonometric equations as well. Yeah, look at this. This one has got like sine of y over 3.35. I'm not going to the depths of it, but having that idea of what those functions represent and what those tools represent, what those small parts represent, and how you can use those tools to make more complex and more intricate machines is going to be a fantastic tool. And Start with the basics. Start with understanding what these functions represent. What are sines and cosines? What are their properties? What are their behaviors? And then you can like use their ideas in making something as complex as this. This took me quite a lot of time to make, but the output of it was quite valuable. And so I encourage like each and every one of you to like at least try your hands on Desmos and GeoGebra. And even if you don't understand, there's a lot of resources to help you out. And there's just always people in the internet that are like willing to help. So do explore.